Hi guys, welcome to our fourth video in chapter 25. This video is going to cover section 25.4 and is all about fission and fusion of atomic nuclei. So we can see again, short list of explanation or short list of objectives here. We want to talk about nuclear fission and nuclear fusion and explain the process by which nuclear reactors can generate electricity. And we've got some vocab words here that we're going to go through. So nuclear reactions are related to energy, and famous physicist Albert Einstein came up with this equation. And this might be the first time you actually work with Einstein directly in science class, which is kind of cool. But Einstein came up with E equals mc squared, where the energy is equal to the mass times the speed of light squared. So this is interesting. This is called the energy equivalence formula. And what this postulates is that energy can actually be converted into mass, and mass can be converted into energy, which is interesting. And just so we know, c is the speed of light in a vacuum, and it is 3 times 10 to the 8 meters per second. It is constant. So in a nuclear reaction, scientists have determined that the mass of the nucleus is always less than the sum of the masses of the individual protons and neutrons that comprise it. So if I take a look over here, this is what's called the mass defect. This is called mass defect. Okay. So if I look over here at a helium atom, well, if I take 2 protons, 2 neutrons, and 2 electrons, and I add them all up, I will get 4.03298 AMU if they're all on their own. When I add them together and squeeze them in to make an atom, and I weigh that helium atom as an atom, I will find that my mass is 4.000260, slightly less than the mass of my individual subatomic particles. And the missing mass is the binding energy that holds that atom together. Okay. Again, that's the mass defect. So and here's what I wrote, right? Applying Einstein's E equals mc squared equation, you can see how the missing mass in the nucleus provides the tremendous energy required to bind the nucleus together. This is also the energy that is released in a nuclear reaction. Okay, so it is this mass defect, the difference in our free particles versus our particles when they're combined in a nucleus. Okay, so let's talk about nuclear fission. Nuclear fission is the splitting of a nucleus into fragments. This is well understood in a sense because we do it very frequently. It's been used for over almost a century at this point to generate electricity. It is accompanied by a very large release in energy, as well as many radioactive and toxic byproducts. Okay, so nuclear fission is what you're probably familiar with from like nuclear reactors. Okay, so if we think about this uranium-235, we have a neutron coming in, and the neutron is fired at our uranium like a bullet, and that bullet hits our uranium where it quickly joins into the nucleus and destabilizes our nucleus enough to make that atom quickly break into pieces. And we get a krypton-92 and we get a barium-141 come out, along with 3 more neutrons plus energy. And these 3 neutrons are important. The energy is what we want. We're harvesting that energy to use it either as an energy source or as a weapon. Okay. Now, if the fission creates new neutrons, this one makes 3, but even if it makes 2, if it makes 2 or more neutrons, it can cause 2 additional fissions. So this can cause further reactions. So what happens is I hit this with 1 neutron. That neutron breaks my atom apart, releases more neutrons. Those neutrons go out and they hit other uranium nuclei, destabilizes those uranium nuclei, which then emit further neutrons, which go on to even more uranium nuclei. This is what's called a chain reaction, where one reaction it causes this reaction to continue happening. And this is actually what happens in an atomic bomb, this uncontrolled chain reaction. In a nuclear reactor, we actually try to control that reaction so that we do not have an uncontrolled reaction. We want it to happen slower. So we do want it to happen, but we want it to happen slower. So they change some things about the reaction to make sure it stays in control. Now, critical mass refers to a sample that has enough mass to sustain a chain reaction. Once you have that critical mass, you have fissile material that can be used in either a weapon or in a energy source. Okay, so we have a subcritical mass where it doesn't have enough, and we have a supercritical mass where it has plenty, right? Okay, So here's a nuclear reactor, and you can see it's actually pretty neat little setup here. We have our control rods, and we have our fuel elements and our carbon moderators. All of this is a setup here to basically control the nuclear fission that's happening in my fuel of this. And most of the fuel is going to be uranium-235. Okay. So most of this set up to control how fast my uranium-235 is decaying. Now, what I do is I will take water, I will pump it in to my system. That water will be heated by the radioactive decay of my elements, and it will boil and produce steam. That steam goes up, goes through a turbine, and turns the turbine. And that turbine generates the electricity. And then the steam goes down into a cooling tower. That's the big like towers you typically see for a nuclear reactor. Those are the cooling towers where the water is able to condense, and then that water can be recycled and pumped back in, or it can be contained in a storage containment pond. Okay. But essentially, what we do is we use the fuel to make steam that turns the turbine. Now, there is a cool type of reactor called a breeder reactor, which actually produces more fuel for it is able to use nuclear fission to create more fuel than it uses. Has a very complex setup, but the basic idea is almost the same, where I have my cooling, my steam generator, I have my heat exchanger here in the middle, and then I have my fissile core. And the real difference is when I have this breeder blanket, which is a type of material that's being enriched by the fission going on. Okay. Again, these are pretty complex, so they would take a little bit more explaining to get into, but they do exist. And that's how we're able to continuously have more nuclear fuel, even though uranium is not very common on Earth's surface. Now, nuclear fusion is much less understood than nuclear fission because we haven't really got nuclear fusion to happen at an industrial scale on Earth, though it does happen in the sun, right? So, nuclear fusion is the combination of atomic nuclei. It can release a large amount of energy and is able to produce valuable materials as waste. We essentially start with hydrogen and we produce helium. And that is the most basic fusion reaction we can do. And helium itself is a fairly valuable element on Earth. Now, that's not all, though, because we can continue to fuse elements together and we can make carbon, we could make phosphorus, we can make other bigger elements, all the way up to even gold could be coming out of these nuclear fusion reactors. So not only does it produce a lot of energy, but the waste is valuable materials that we could use in other things. So it doesn't really have waste. Now, these fusion reactors are also known as thermonuclear reactions, just so you know, because they release so much energy. And you can see this actually is the nuclear process that's happening in the sun. I have an example here where you see our two hydrogens combine to form a helium atom. Although they'll combine to form a proton and neutron first. Then another proton comes in, combines with it, and then that proton will collide with another group of protons and a neutron to form a helium atom and two free protons, which are free to then go on and continue to react. So this is a simplified diagram of how fusion occurs in the sun to go from hydrogen to helium. Okay. All right, guys, that's all I have for this video. Thank you for listening, and I'll see you in the next one.